Vincent, are you going to remind them about the
Yeah.
submission of the docs? Okay.
Yes.
All right, then I'll mute my video and I'll just stick around for the first few minutes then and let you.
Yeah.
Start.
Thanks, Andrew.
Mhm.
All right. So people are still connecting, but maybe a few words. So sorry for the delayed small technical problem. And then, so I forgot to explain a bit about the program. So the reason is that last year Raul took the first week and then I took the second week. And last year Raul explained everything before I start talking, but this year it was me, the first speaker, and I forgot to explain that. So this program runs until mid-end of August, with like a webinar every week on nuclear theory. Now, if you want, so the participants are actually invited to, at the end of the program, to write kind of a summary, a couple of pages, 4 or 5 pages, about what you have learned. So what you have learned can be some words, some writing about, what you found useful, new things that you learned. Can be some exercises, some small research project that you did during these weeks. Anything that is relevant for this program. Now, in order to prepare this, you can submit every week a couple of something to write. It's optional, it's recommended, because then at the end of the program, then you have already what you wrote every week. As I said, can be an exercise, can also be like a couple of sentences about what you liked about the lecture. It's really up to you. Let me see. Here we have a question. Yeah, so you are invited to submit something every week. Now, if you cannot one week for whatever reason, it's okay. It's just for you to prepare the final report. The final report, I mean, if you just want to join the webinar, fine. The report is mandatory if you want to have this certificate of participation. So if you want to have just a certificate saying that you participate to this program, we ask you to write a couple of pages. It's totally optional, it's totally up to you. And to prepare that, we invite you to write something every week if you want. There will be at the end of the program also the option for, totally optional if you want, just to give a 5-minute presentation. And if you volunteer, then we'll make a schedule, and then you will have the possibility to speak for a couple of minutes. All right. So yes, exactly. So again, the same. So you should have access to the Dropbox, and the Dropbox should be fairly organized. Let me check if there is like a write-up for lecture 1, student submission. Feel free to you can create a folder with your name. That will probably be the easier. You create a folder with your name where every week you just upload your document if you wish. That's maybe the easiest. If you have technical problem, just contact us. We'll try to see if we can fix that. And then the same thing as, okay, yes. Same thing as last week. Write your question in the chat, and I will try to answer them as I see them. Webinar chat, okay. So when I see a question, so feel free to interrupt me. Hopefully I will be a little bit shorter than last week. So I'm going to start sharing the screen. Okay. So does the final have to be typed in or handwritten? I think typed in is just easier to read. I don't know, Andrew, do you have?
Yeah. So hi, everyone. I'm Andrew. I'm one of the other members of this program. Um, we would prefer if it was typed, just to make things easy for us on this side to read and process everything. Again, we're not looking for very long reports here. They're supposed to be these weekly ones are more geared towards what you could find interesting, or little exercises you work on, or just a couple paragraphs, and then the final report must be typed up for sure. And you can use whatever word processing software you'd like. We just want the please submit a PDF in the Dropbox, just because all of us use different software to read these documents, so that just makes it universal for us.
Yes. All right, thanks, Andrew. I'm gonna start sharing the screen, and we're gonna continue where we left off. So if I summarize what we've seen last week, we started from Rutherford, who actually was really the pioneer of particle physics or nuclear physics in general, finding these alpha rays. He started making beams out of them. In doing that, he realized that he needed to compute what is a cross-section, just to compare a model of understanding the nature. Here, the understanding that he had is like, well, we have a charged particle that interact with a Coulomb interaction to like a nucleus. Of course, before that, we saw that the nucleus, the discovery of the nucleus was like thanks to Rutherford. Right? And then he derived this cross section. Now, I recently learned, like actually yesterday, that Rutherford might not be the guy who derived that. He was helped by some mathematician. Yes. Looking at the chat at the same time.
Sorry, I'm posting some info for them.
Yeah, no, it's fine. It's fine. Yeah. So now, based on that, and then you see that there were like some very nice comparison between the theory and an experiment, and up to a certain point. That point was actually the interpretation of this failure of the comparison was that the hypothesis that the alpha particles scatter was no longer true. As you increase the energy, the alpha particle penetrates the nucleus, and then it does not scatter. So of course it's not Coulomb interaction, it's something different. So that's why there is a discrepancy between the theory who assumes scattering and then the data who is no longer scattering in this case when the energy increases. Now, the energy where that separate these two regimes corresponds to the energy for the particle to actually arrive to the nucleus. Now, this energy is actually the energy required to fight against the Coulomb barrier. And the Coulomb barrier depends on the radius. So from this energy, we can actually deduce the radius of the nucleus. So Rutherford did that and found the order of magnitude was like 10 to minus 15. What do we need to write about this project? As we said, you can write about what you've learned. It can be words, what you found interesting. If you did an exercise related, either the exercise we proposed, either a related exercise, somebody actually derived this cross-section very nicely. It's not an easy exercise, but it was nicely written, very nice. But it can be something like that. Doesn't have to be. It can be also, what you've learned. Couple of, what you take out from this lecture, right? All right. So now, what's next? So after that, Rutherford starts using his alpha beam basically on anything. He realized that when you shoot, quote unquote, shoot alpha particles in the air, he was observing isoniation, a particle with a positive charge, which looks very much what we would expect from the elementary particle of the nucleus of a hydrogen, what we call a proton. So he said, well, it looks that when I shoot alpha particle into the air, I get something that looks very like a proton. Why such? Then he realized that it was not the air itself, it was actually the azote, the nitrogen in the air. So by isolating the nitrogen, shooting alpha particles to it, indeed you create oxygen and a proton. So that was like, quote unquote, the discovery of the proton, with, again, at the lab. Similar processes, the discovery of the neutron was made by Chadwick, or Chadwick was actually working in the Rutherford lab when he made that. And he noticed that by shooting alpha particle into beryllium was creating a neutron. So the beryllium is very particular because you have a lot of neutrons. He has 5 neutrons and 4 protons. It's still nowadays one of the best ways, if not the only way that we produce neutron, is by using beryllium. Beryllium very naturally emits a single neutron. Okay, no more question in the chat. Good. All right. Now, so at this stage, of course, it take more than a couple of seconds, like we're going fast in time here, but in parallel, people say, well, if the nucleus is composed by protons, and all these protons are positive charge, then the neutron are neutral. So why the proton, they bind together with neutron into a nucleus? They are positive charge. They should repel each other, right? So that means that there should be another force other than electromagnetism that actually bind the proton, that attract the proton such that they stay together in the nucleus. Now, one way of seeing an interaction, a force, is by exchanging a mediator. So the electromagnetism, positive and negative charge, interacts via emission of photon. Photon is the mediator of electromagnetism. So if there is a force that actually happens between the nucleus, or between the nucleon into the nucleus, then that force must be mediated by something. And there was like a theorist called Yukawa who actually formalized that in 1935. So just after the discovery of the neutron. And then at this stage, it was totally an invention. Like it theorized the invention of a particle called the pion, called pi. There's some historical reason of why it's called pi, and then this particle was supposedly the particle who was mediating between the proton and the neutron. He actually made a prediction about the mass and the charge of this particle. And that particle was actually observed a couple of years later. So where was that observed? So it was observed first in India. So people realized that one way of observing particles or new particles was observing cosmic rays. So what is cosmic rays? You imagine that you have a nuclear reaction that happens in stars, in the core of the stars. So those reactions creates particles, cosmic rays. They are rays of neutrino, protons, electrons. Of course, other particles can also happen, but those they will decay eventually. But the proton is stable, so the proton flies in space, and space is mostly vacuum. So those protons, they scatter until they meet something. So when they reach Earth, there is the cloud, there is the atmosphere. So these protons meet other protons. And from this is a very high energy scattering. You have a very high energy proton coming from the space, hitting the protons from the oxygen and other elements in the atmosphere, and creating other particles. People realize that even they were going in the higher they could go, like in the mountains, be close to this shower, cosmic shower, it was called, Then they would come with photovoltaic panels, like detector, and then observe new kind of particles. And they knew that they were looking for a particle of the order of 140 MeV. So we talked about MeV last week. And then they did observe a charged particle with the same mass. Now, and they say, oh, we found the pion. Actually, what they found was another particle called the muon, a particle that did not participate to the nuclear interaction. Only, it's called a lepton, it participates to only other type of interaction. So this muon was discovered by expedition by team of physicists, Indian physicists in India. It was also carried by other people in Europe a bit later. Eventually, they found pions. They first found the muon, then they found the pion. So let's see. So who discovered the proton? It's Rutherford. If I remember well, is Rutherford. Rutherford by the proton, by realizing that it was from, I don't know what was that song, but yes, by shooting particle at the hydrogen. Okay, are we submitting the page? Are we submitting the page weekly or the end? It's encouraged to submit every week. Okay. Just to prepare the end report. All right. Okay, so now what we have, yes. And then later, the pion was actually produced in a lab by colliding alpha particle into carbon atoms. Okay. All right. Oh, so this was in the slide. It's just that's supposed to be finishing my first part that I could not finish last week. So there was like a small exercise about dimensional analysis. It's just an interesting exercise. The story is there. There's a story about that. Is a guy who actually a British physicist who's from the picture of the bomb could guess what was the energy of the bomb. It was a secret. It was a secret. The American physicists, they bragged about making a bomb. They didn't want to disclaim what was the energy of the bomb, but by a very easy and interesting exercise about dimensional analysis, they found the power of the bomb. So the whole story and the answer is here. So you can give it a try yourself, and then see the solution. Another exercise I was proposing, also totally optional, is just to compute the radius of these elements based on the formula that are in the slides. You can also compute the energy of the kinetic energy of the alpha particle. You will see that they are fairly slow compared to the speed of light. Right? Part two. All right. So at this stage, the world of particle physicists, particle physics / nuclear physics reduces to proton, neutron, pion. They all proton, neutron form really nucleus, and they exchange pion. And people realize that the proton and the neutron, they're pretty much the same mass. And all the pions, they have the same name, but they are different particles. They have different electric charge. But, you know, Heisenberg, who is a famous physicist as well, he said, well, they only differ by the electric charge. So maybe I can understand this particle to be actually the same particle if I could unplug the electromagnetism. Like if I could unplug the influence of electric charge in the world, then maybe the proton and the neutron would be the same particle, right? This is called a symmetry. And this symmetry, he called that the isotopic symmetry, because this is something related to isotopes. And now we call that isospin, because it has to do with something which is called a spin. So it was called isotopic spin and then isospin. So the name of this underlying symmetry saying that from the nuclear interaction, a proton is exactly the same as a neutron from the point of view of the nuclear interaction. This is called the isospin symmetry. can we also address our doubts in the report? Yeah, sure. Yeah, yes, of course. Yeah, yes. Yes. Same with the pion. All the same particles. So respect to the nuclear forces, they are the same particle. Why there are why two nucleon, why there are three pions? This is a property, there's some math behind these symmetries. So every time you have a symmetry is very important in physics. There are two very important concepts in physics. One is dimension analysis, that the exercise that I found. The other one is symmetry. Symmetry plus dimensional analysis is 99% of the physics, basically, in practice. So we call the proton and the neutron, we refer them as nucleon in general. And then those are called pion, right? There will be later on, we're going to do some scattering of pion to neutron. So now we can produce pion. We saw that with carbon atoms. So they have a charge, so we can actually scatter them on a proton. And when we scatter them, we see what we call a resonance, something that a very short-lived particles that we call delta. Again, the names, they were made up like that at that time. And then this delta lives for a fraction of a second, fraction of the order of 10 to minus 10, 10 to minus 11 seconds, something like that, and then decays back into 2 pion. Because there is an underlying symmetry, that means that a proton is the same as a neutron, a pion neutral is basically the same. There is some group symmetry behind that can actually give you what will be the result of a reaction compared to another one. Example, if you know what's the rate, what's the cross-section for a pi zero scattering into a proton, then this thing is going to be twice as big as the scattering of a pi minus to a neutron, just due to the symmetry. And this symmetry is called isospin, right? So why I insist, because we're going to see that the generalization of this symmetry will lead to the understanding of what we call quarks now. All right, so in parallel, people, they were still looking in the sky, in the Pyrenees, in the Alps, in the Himalayas as well. And people would bring cloud chambers, so chamber were under pressure, where you have a liquid very highly under pressure, and then when a charged particle crosses that liquid, it just gives a lot of bubbles, bubbles that are recorded. Take a picture of these bubbles, and then you have a track. Those tracks typically are very difficult to analyze, but people develop like expertise in that. So out of this picture like that, so those are real pictures that come from this lab, this website, and they were noticing new particles. Of course, for us, it's very difficult to see them, but they're there, okay? And that thing leads to called a delta particle could decay into 2 pions. Those are pions. They say, oh, we have a particle decaying in 2 pions. And then people say, well, that particle is very similar to a particle that decays into 3 pions. Before it was called tau. This one was called theta, this one was called tau. You have a quote-unquote tau particle that arrives, and then here decays. So it lives for a couple of micrometers and then decays. Now you can see this K shape was very particular, and then actually led to the name meson K, and then after kaon. And then nowadays we still call that kaons. We do not record that. We have more sophisticated methods to actually record the decay of particle. So we don't really see a K form in the detector, but the name stayed. I mean, and you can see it's kaon interaction. I mean, so kaon, the name kaon was what we call a mesons, And those mesons, as we can see, they had like kind of weird / strange properties, and the name strange actually stick. So though this meson is what we actually call a strange meson, and strange as a really well-defined, that really means something precisely in physics. They were observing another quote-unquote strange particle. Like here, this is in a cosmic ray. You have a collision here. You have different particles that are scattered. And so you can see that here there is a neutral particle. Why do we know that it's neutral? It's neutral because there's no track. And then here we see a proton. So they know it was a proton because they had some technique to actually identify particle. And then this one was neutral. It was a particle that they later called lambda 0 for neutral, that would decay into proton and pion. With a life which was longer than expected. So the life of typical resonances is typically 10 to minus 23. So it's even very, very, very short. So, but that one was 10 to minus 10. And you can see it traveled a fairly amount. I mean, it travels some micrometers, right? So of course, the longer it lives, the further it travels, right? If it was traveling 10 to minus 23, you would not see them. Here, you would, everything would collide to a point. But we do see them, right? So all this was another quote-unquote strange property. Why do cloud chamber use pressurized liquid? I'm not an expert in that. You probably will find some information on internet. But this was the technology, one of the first technology was used to record charged particle. I don't remember the exact details, so I'm just gonna let you answer. Just look for information because I don't know exactly the reason for that right now. So, and then all these particles, they were these very weird / strange properties, and people try to make sense of that. Physicists, they like something well organized. So Gell-Mann was trying to design a classification scheme. So how can we actually understand those things? And he published a paper called isotopic spin. So isotopic spin is isospin, as we see. And new unstable particle. Alors, by new unstable particle, he meant strange particle. And then you can see, he said, okay, that's what he told afterwards. He said, I wanted to call that isotopic spin and curious particle, but they rejected that. So I tried strange particle, and they rejected too. They say now, new unstable particle, very, very conventional. So the story is actually written there, right? And there were more and more strange particles. There were 19 that we call now strange particle. And they would always appear in pair. They would always have a longer life expectancy. So can we use cloud chamber to detect cosmic microwave background? I don't think so. I think the microwave background, you need something much more precise. Yes, so answer live. All right, so there were another particle who came up just after that, like in 63, called the phi. The phi was observed in 2 kaons. So the kaons, you remember, it's the meson K, and we saw the K tracks. So they would notice that there would be a new particle that would always give 2 K tracks. And they say, well, but that particle, if it decays into 2 K tracks, 2 K mesons, it should decay into pions. I mean, why not? And it was not observed. They say another strange property. Say why that particle doesn't like pions, and then you can see that the transition now. Before we needed only a couple of events, the K meson, only a couple of tracks, and you would identify a meson. Here, the technique are a little bit more advanced, and we have about 40 events. So all the phi meson are here. So we have 38 events with the same mass, of a mass about 1 GeV, that decay into 2 kaon. All right, so another quote-unquote strange meson. So Gell-Mann actually made sense of that. So now the resolution of all these properties is that every meson, which was not known at that time, all these mesons are composed into 2 quarks, and here you have 2 quarks that are light. They are called U and U for up and D for down, and that one possesses a third type of quark that later we call strange quark, because it has led to all these strange properties. So the reason this guy is actually a strange anti-strange quark meson that can only decay by leaving a strange non-strange meson. The 2 strange quarks are present into the kaon, but they are not present into the pion. So that's why the phi decay into 2 kaons. So the symmetry that the pion obey is a symmetry of what we call of order 2. It has to do with rotation. Rotation in 2 complex dimensions. I know we're not going to talk about the math. You may see that in group theory. It's called isospin or angular momentum. It's the same group, the same symmetry group. Okay. Then Gell-Mann had some background in mathematics, in addition to physics. He was one of the only rare physicists who knew group theory. And he said, well, what if I actually generalize the group for isospin, for the pion, instead of having 2 dimensions, I put 3 dimensions. Something, might seem a bit crazy or artificial. But this leads to prediction and to classification of mesons. Now, we're not going to explain that, but if you have 3, and then you couple 2 types, so you have 3 times 3, you have 9, but those 9, they're actually split into 1 plus 8. So we know that 3 times 3 is 1 plus 8. Group theory tells you that when you take 3 of those and 3 of those, 3 times 3, you get 1 and then 8. So you get the 3 pion, the 4 kaon, there are 4 kaon, and you get 2 extra mesons that are called eta. They were discovered just after that. And one of the eta is the singlet, 1 is called a singlet, and 8 is called the octet. So the octet is composed by 4 kaon, 3 pion, and 1 eta. I know it looks artificial, but everything made sense. So what I mean by everything made sense is that there is a well-defined mathematical symmetry group underlying this, and then the consequences of this symmetry was some properties to the meson, and those property was observed in experiment. So there were like some empirical evidence that the underlying mathematics was true. It's just that at this stage, nobody had any clue of what was the physical meaning of this mathematics. Why? What the hell is this symmetry of order 3? It's only later, and I won't have the time to discuss that, maybe Wyatt will talk about that, that later people discovered there were quarks, like every meson is actually a pair of quark and antiquark. So that's why when you have a quark and an antiquark of 3 different flavors, you can form 9 mesons, because 3 times 3 is 9, but they are classified according to 1 plus 8. Now you can tell me, well, what about 3 quarks? Because a baryon Oh, okay, so that's the meson. A baryon is, later we discovered that baryons is actually 3 quarks. So we could actually organize the 3 baryons into 3 quarks. So when here you have 3 times 3 equals 1 plus 8. If now you do 3 times 3 times 3, you're going to get 1 plus 8 plus 8 plus 10 plus 10 plus 27, something like that. So there is an octet, and there is also a decuplet. So let me see the question that we have now. All the symmetry were conserving the isospin. Yes. So isospin were almost exact symmetry, very good symmetry. The strange symmetry, the SU3, the one at 3 dimension, is partially broken. And we're going to see that in details. So if the symmetry was exactly the same, all these particles would have the same mass, and the eta prime would have a different mass. Now, the eta prime does have a different mass than this octet, but the 3 pion have the same mass because the isospin is almost exact, but the kaon, they have a mass slightly different from the pion because the symmetry, this octet, is slightly broken because the strange quark has a slightly different mass. When you do that with, so what actually Gell-Mann did, as you see, we're going to check this Gell-Mann-Okubo mass relation, he said, well, if I know group theory, now if I organize these baryons according to some group theory, I don't know why, but it does work. So I still don't understand why, but there are some nice property with this. Like for instance, they look like the neutron and they know that the neutron and the proton, they have the same mass. And they have strangeness 0. They are not strange at all. And then their mass can be described by this formula, well, whatever that means. Now they say, okay, now I have baryons. You remember the lambda is 1 time strange, actually -1, but whatever. It has like 1 strange property. There are some particles who are double strange. Why do we know that they are double strange? Because this one actually decays into this one, who actually decays into this one, right? And then when people notice that when you jump for an horizontal line to another one, the mass actually grows by the same amount. So when you go from here to there, or from here to there, it's actually the same shift. I don't know if, yes. So they say, well, it looks like there is some things behind this symmetry, you know. So this is the baryon octet. There's also a baryon decuplet. It's 10, but there were only 9. So it's a group theory tells you that there should be also a decuplet. There should be 10 baryons. At the time, in the 60s, there were only 9 here. There were the 4 delta that we talked about. There were the 4 sigma star, whatever that name, and there's the psi star as well. And there's like about 150 MeV of difference. But the theory say, well, there should be a 10th baryon. So Gell-Mann made a paper. He said, I'm predicting here a baryon. I'm going to call it omega. What I'm predicting its mass, because I know it's going to be a jump of 150. So I know the mass of this guy, I know the mass. The electric charge, every time I jump for a line, I'm losing an electric charge, plus, plus, plus 0. That one should be minus. So I know the mass, I know the electric charge, right? So he sent them to experimentalists, and then 1 or 2 years later, at the exact same mass with the exact same electric charge, they found that particle. Boom, Nobel Prize. So the theory prediction was correct. So let's see. So this was the actual observation of the omega baryon. So the question, the $1 million question is, can you spot the omega baryon in there? Of course you cannot. I mean, it's very, very, very difficult. I mean, you need, so we can actually simplify and see, because you know that also we only see the charge track, right? So when we clear this up, this is what we find. So the omega is actually this line here. This is the omega, right? So this is a pion. They could know it's a pion. They could determine the mass. Here you see here that omega decays into a pion and then a sigma that you don't see. It's a neutral one. And then that guy decay into a gamma. You don't see it. It's neutral. Then you see a lambda. You don't see the lambda. You have to go up till here. And then here you have the pion and the proton. It's not easy to know that this guy is related to this one. But they were expert. I mean, that was their job. So those, and then you can see it's 3 times strange because he decays into a double strange. That double strange decay into a single strange, and that decay into a non-strange particle. So this now is called to strange cascade. That's the name that we employ today. So, and then the cascade is here. Oh yes, I voted strange cascade, right? All right, so that was, and I think, yeah, that's more or less summarized. I think that's pretty much the end of my talk. I wanted to arrive to the discovery of the omega meson, and that was really the birth of the quark model. That I don't have the time to enter into the details, but we actually started from Rutherford till the omega mesons, really the beginning of nuclear/particle physics, the very birth of the quark model. Let me see if I have other thing. Yes, I have nothing else on this. So what I can do is that actually this week, there were a talk that I started watching by David Gross. So David Gross is the director of the Keep Institute in Santa Barbara. He's a Nobel Prize winner of 2004 for the strong interaction. He was asked to give a talk for the 50 years old of the birth of what we call quantum chromodynamics, who was actually developed in the 73. He actually started also by talking about Rutherford. So in the email, I will make an email with the link to this talk. And I have also another historical talk from 10 years ago by Zweig, who was also, Zweig was Gell-Mann student. And then Zweig actually in this talk for the 40 years of QCD this time, actually talk about his relation with Gell-Mann, how they came to the invention of discovery of quarks, and all other anecdotes. So they were actually fairly entertaining, these talks. So I'll share them with you. So question, learning all about this discovery and methodology is highly inspiring. Thank you. All right. Are there any other questions in the audience? So we still have a couple of minutes before people join. So don't hesitate to ask your question. I hope it was clear. Of course, there are so many more things to tell. I mean, I barely scratched the surface. We barely, I mean, I mentioned quarks many times, but I did not really explain that properly. That was more like some historical consideration here as an excuse to introduce some basic physics concept. Yeah, so let's see. If there's nothing else, then I'm going to stop sharing. I think the people from the next lecture, I think that, I don't know what's in the program. I don't know if there is another. What should we write in the report? It's very up to you. As we said, the report, we encourage you to write a very short weekly report just to facilitate you to write these 4 or 5 pages at the end of the program. There are a couple of exercises in this slides. You can do them, you can write them, you can just write a couple of words of what you've learned. If you found some interesting references. Somebody asked about a good book for introductory nuclear physics. I found one. I'll send it over as well. So really, it's really up to you. It's whatever you found beneficial for you. You can write, can be just a couple of lines, whatever. Really, are these different particles explained using field theory? If yes, then what kind of fields for pion, let's say? Well, so field theory came after that. Well, it came in parallel, but it's so there are different ways you can actually describe particle. Here we always kept like some very classical picture. Quantum field theory is really like a tool to describe nature. We focus more on the empirical evidence. The mathematic or the formalism can be all these particles. We can try to explain them with some classical properties. We can also make some quantum mechanics properties, and then eventually people realize that really for the fine-tuning they needed like a new theory. Because in quantum mechanics you cannot create particles. If you really need to have destruction and creation of particles, you need what we call a second quantization, and then it was the origin. But all this is really beyond the scope of this webinar. Those are the mathematics beyond the theories. Can we choose one topic and go depth for the report? Go ahead. You know, if you like something, it's really for your beneficial. Like Andrew, go ahead.
No, I just wanted to add for the person asking about the field theory and pions. I appreciate your answer because I know it's a tricky subject.
Yeah.
That ultimately we think all of nature is described by the standard model of particle physics. So in principle, we should be able to calculate these pions from there. And that is an active area of research because the theory is, as Vincent said, it's beyond the scope of these lectures and mentoring program because it's very involved. But if you're interested in kind of that area, I invite you to do some elementary research on the standard model. And, as you continue on your scientific careers, you can
one misconception. Yeah, one misconception also is that people they think that they can jump into quantum field theory like that. An advice is like you really need to master quantum mechanics first. So it's much better just to go step by step, understanding classical mechanics than quantum mechanics. You want to walk before you run. You want to learn. And then there was another question that just disappeared.
I answered it. It was just about citing sources. I said,
yes.
Yeah.
Yeah, exactly. Yes. Please do cite your sources, right? And I think it's like 6 p.m. here, 12 in the East Coast. And
I think we need to move on for the Python people.
Are the people for the next lecture ready?
I say Yvonne here. So
all right.
Yeah. Hi, everyone.
All right.
Thank you, Vincent.
Thank you.
Bye-bye, everyone.
So should we just jump directly into Python? Or does anything tech have to happen for the live stream?
No, just I'm sorry, but today is just like rolling right into you.
Okay, awesome.
Your presentation. Yeah.
Okay, great. That also works. Okay, hi everyone. Hello. Well, I'd say good to see you all, but I cannot see you. But I hope that you're all doing well. I hope that everyone is very engaged from what you just learned. And yeah, we're just gonna go straight ahead to our discussion of calculus and how to use Python to explore problems in calculus and yeah. Okay, so let me maybe just start with the PowerPoint presentation. Okay, So let's maybe go back a little bit and remember what it is that we learned. And maybe let's remember what we learned last time by exploring again my favorite example, which is the harmonic oscillator. Since you guys were just thinking about quantum field theory in a second. Oh wait, let me make sure that I've added everyone as a panelist. It should be. Give me a second. Sorry, just give me 1 second. Okay, let me stop sharing. I'm sorry, I'm not being able to promote people to panelists. I could do that last time, but this time I'm not being able to. Beth, can you promote people to panelists?
I think so.
Can you help me promote Adriana in the chat? They mentioned that they were gonna that they're a TA for this session. Hi, Adriana. Thank you for helping us today. I appreciate it. So hi. So yeah, everyone feel free to also put questions in the question box, and Adriana will either answer them if they're quick, or we'll pass them up to me. So yeah, don't stick with questions. I'm sure that whatever question you have, other people will find it useful, and we highly encourage you all to ask questions. Okay, awesome. So let's review a little bit about what we did last time. So we were considering this harmonic oscillator, and as we said last time, this is really the fundamental example to understand really in all of physics, right? The harmonic oscillator, for many different reasons, right? On one hand, when you learn a little bit about energy, you learn that every minimum phenomenon is kind of like harmonic oscillator. So every point of equilibrium behaves like a harmonic oscillator for any physical system. That's sort of one sort of very broad reason why. Another reason that is really important is because in physics, sometimes we, as we're used to, so somebody asked me to share the Colab notebook link. Yes, I will. I can share that. Give me 1 sec. When I open the Colab, I'll send it. I'll send a link to it on the chat maybe. Okay, so sorry, what was I saying? Just to double check, do you all have access to the slides? They're posted on the Dropbox, and I was under the impression that everyone had access to the Dropbox. Can somebody confirm if you have access to that Dropbox? Okay, awesome. So on that Dropbox, you'll find some code as well that I use to prepare for this session. But I will also send afterwards my live code. I'll also put it on the Dropbox. Okay, awesome. Okay, so that's one thing. Another reason is that maybe in the way we learn sometimes in undergrad or in high school, we tend to sort of learn things in too much generality. And I am a true believer that you can learn really, really difficult things as long as you stick to the simplest examples. And it is a really fruitful way of learning to rather than attack things in full generality, understand examples in a lot of detail and understand the minutiae of examples, and then being able to extrapolate from the examples that you understand into other situations. So let's focus on this example. Right, the comment that I was going to make about quantum field theory is that quantum field theory is just a bunch of harmonic oscillators stacked on top of each other. They're like an infinite number of harmonic oscillators, but that's what quantum field theory is all about. So if you're interested in particle physics, understanding a harmonic oscillator is so crucial. What the harmonic oscillator is that it's just a spring system. It's an ideal spring. We have some spring attached to the ceiling, right? And there's a box at the bottom of that spring, and that box has sort of equilibrium point, and then it oscillates up and down, up and down, up and down, up and down. The mathematical form of that oscillation, and this is something that you might explore in the differential equations part of our set of lectures, is this one, is this form. Maybe it's worthwhile to just stop for a second and just make sure that everyone understands what this equation means. So let me maybe share a notebook. So the position of a harmonic oscillator. So this is our oscillator. Here's the wall, and the harmonic oscillator has a spring, goes down from that wall, and it's going to have some equilibrium position over here, right? So if the box was over there, it would be in equilibrium. But in general, the spring can be, let's say, for example, stretched, right? And the box might be out of equilibrium. Can't go for some reason. Okay, good. And then we will describe the position of this box by some distance x of t. Sorry, I also need to promote someone else into TA. Beth, could you help me promote Declan also as a TA? Thank you. Thank you. Hi, Declan. Thank you for helping us out. Okay. So what is the fun? So we're gonna call negative if it goes down and positive if it goes upwards, just to choose a convention. And as I was saying, the position as a function of time looks like a times the cosine of 2 pi divided by this constant t times t. Let me rewrite this in a, so what does this mean? This means that the position, if I was to plot it as a function of time, t starts, well, you know that at t equal to 0, the cosine is equal to 1, right? So it starts at this value a. I'm going to assume that a is some positive constant. So it starts over here. And then let's say at t equals to 1 to t, or let's say to t divided by 4. So at t divided by 4, well, let's see, 2 pi divided by t times t divided by 4 is equal to pi halves, right? And that is the same as 90 degrees. And the cosine at 90 degrees is equal to 0. Because at 90 degrees, you have a point that is completely vertical. It has no horizontal component. So this is over here. So this is, if you want to think of it, the cosine is useful to think of it in the setting of a circle, right? It's a useful way of thinking about this, right? So the cosine of some arbitrary point, remember, is this distance, right? So this is a circle of length. If this angle here is theta, and this has unit 1, then this is the cosine of theta. So all that I've been saying is that theta in here is 2 pi t divided by t. Sorry, t divided by big T. So when little t is equal to 0, theta is equal to 0, and we say that at this point the cosine is equal to 1. At t equals to t4s, we have theta equal to pi halves, which means that we're over here, and there we see that the cosine of theta becomes 0 because there is no horizontal component. And then at t equal to t halves, we have theta equal to pi, and at pi we're over here, so we have the cosine of theta equal to -1, which means that x is equal to -a. So I drew -a over here. Then let me just draw some straight lines over here just to guide myself. So then our position is over here, and then at 3t quarters, this is equal again to 0. And then at t, we're back to 1. And you all know this graph, right? It sort of looks something like this. And so on, right? So that is the harmonic oscillator example. And something that we're going to do, and that computers do really well, is to try to write this in dimensionless quantities. So in here, A has units of meters, or dimensions of length, which means that X has dimensions of length, which means that X divided by A is dimensionless. This has units of 1. Right, so there's a number that in any units that I computed, whether I decide to express X and A in meters, centimeters, kilometers, inches, feet, it's going to give me the same value. And the same we can do with the quotient of t divided by big T. By the way, big T is precisely that time that it takes for the oscillator to go all the way to the top, to all the way to the bottom, to the top again. That's T, of course. So we can rewrite this. Let me just rewrite this in this form. X of t divided by a equals the cosine of 2 pi times t divided by t. And this is really what we're going to be plotting here. Okay, so let's take a look at that plot again. Okay, so that plot was this one over here. That is the plot. And notice how instead of having a and minus a here, now we have 1 and -1, because instead of plotting x, we're plotting x divided by a. Similarly, the period now, instead of being big T, is equal to 1, because we're not plotting little t, we're plotting little t divided by big T. And as we saw, the way to interpret this graph is that it's giving us the behavior of the position in time, which we can also look in this film, right, in this video. And you can find the code for how to build this sort of films on the Dropbox. Okay, so as we saw, something that we're interested in studying is the way that the velocity behaves, right? The rate of change of this particle. So something that I want to notice, everyone to notice, is the fact that between here and here, the particle is moving quite fast. And I hope that everyone is seeing that, right? The position of the particle is changing a lot real quick. On the other hand, between here and here, the particle is moving really slowly. Like it's only changing this bit of distance, right, between here and here in a long amount of time, while in here it changed in the same amount of time. It changed from here to here, right? So it's a much bigger distance, and that is correlated to the slope of this graph. So in here I'm plotting the slope. So in this region where it's going really fast, we can see that the slope is really inclined, right? In this case, it's very negative, meaning signaling to the fact that this particle is moving downwards. On the other hand, in here, once the particle starts going kind of slow, the slope becomes a lot more horizontal, right? And that is signaling the fact that the velocity went down. In here, the slope is once again very high. The particle is moving really fast comparatively. And the slope was positive, corresponding to the fact that the particle was moving upwards, and so on and so forth. Okay, so that is our harmonic oscillator example. And we can also plot the velocity. In here, as I was claiming, the velocity is really high, right? The velocity is really high in here. We have a really negative slope, and indeed the velocity is -1, which is the highest it will ever be in the negative direction, of course. On the other hand, in here, when we were going really slowly around here, let's repeat that. So here, when we're starting to move really slowly, the velocity is very small. It's very close to 0. In particular, over here, the velocity is pretty much 0, right? And notice something really interesting. This is also the lowest point the particle will ever reach, right? So that is something really important that we will comment on afterwards, which is that whenever the particle is at its lowest or its highest, the derivative is going to be equal to 0. Okay, so this is it for the velocity plot. Now, we also saw that we could play the same game of figuring out what the slope of the velocity plot itself is, right? So in here, for example, the velocity is changing really quickly. Now the velocity is changing very slowly, which means that while this particle is moving quite fast in that region, right? Here in the middle is moving really fast. It's moving pretty much at constant velocity. It is a pretty high velocity, but it's pretty much constant in that region. And now the velocity is changing really fast. When it's in the minimum, where it's moving really slowly, the velocity is, however, changing really fast. It goes from being negative to being positive. So it moves really fast. And this is all encapsulated by the concept of acceleration, right? So we can do this same thing and now plot the slope of this graph, which is the acceleration, over here. And we can see, for example, in here, where it's changing really slowly, the acceleration went through 0, and so on and so forth. And finally, let me just remind you of the fact that we noticed that we could interpret this plot of acceleration not in terms of the velocity graph, but in terms of something a lot more intuitive, which is why in physics we think so much of acceleration, which is that we can interpret the acceleration plot by thinking not of what the particle is doing, but thinking of what the spring is doing, thinking about the way that the spring is reacting to the particle. So, for example, over here, where the acceleration is going to become 0, right? Where when it becomes 0, the spring is at its equilibrium position. The spring doesn't want to move there. There are no forces on the spring. On the other hand, when the particle is when the acceleration, sorry, I'm having trouble making this work. When the acceleration becomes very negative, for example, right? We see that the spring is pushing downwards really, really high because the spring has been compressed completely. Now the spring really want to push in the downward direction. That's why it became so negative. On the other hand, when it becomes really positive, the acceleration, that's because the spring is pulling upwards really fast. And that is the content of Newton's second law, that the force is equal to them, is proportional to the acceleration. Okay, so that this was all review. Let me just stop to make sure there are no questions about this. Okay. Okay, good. And as we mentioned, there are derivative tables, and it's not too hard to take derivatives analytically, but in here we're interested in learning how to take derivatives using a computer, and we can take these derivatives by defining a function, right? Which takes the derivative of point x of the function f using a step delta. Remember, we want to take delta to 0, but a computer cannot do that. So we're going to just take delta really, really, really small. And we can compute what the change in f is between x plus delta and x. This is the change in f, the numerator, divided by the change in x. And the difference between x plus delta and x is just delta. And that's how we compute the derivative using this function definition. And in here, I gave you various examples. We worked out one in live. And in here, I wanted to just show you a lot of examples. So the sine function we have studied very well. We studied a really close cousin, the cosine of that function. And you see, I can plot the derivative for various different choices of delta x, right? And sorry, this is not the highlighter. This is the laser point. For various different choices of delta x. So for example, if I choose delta x equal to 10, there's no way I'm going to get the right answer. I just get some oscillation. And as we gathered from our intuition of the harmonic oscillator, as long as we choose the units appropriately, the derivative should have also amplitude between -1 and 1, right? And this wave clearly does not have that amplitude. So if we choose delta x equal to 1, we actually get a much better result. Which is this orange wave, which has a much bigger amplitude. And which if we choose delta x equal to 0.1, we have a much better result, which is this green line, which is barely visible. Why is it barely visible? Because there's a red line on top, which is equal to the cosine of x. In here, what I'm doing is that I actually know what the answer of the derivative of the sine of x is, so I just plotted it without any approximations. And what we can see is that doing an approximation with delta x equal to 0.1 already gives us a really, really good answer to what the exact answer is. And we can do the same game for example, the exponential function. The exponential function looks like this on the positive real axis. And in here, I'm plotting its derivative for various sizes of delta x. Again, delta x equal to 1 doesn't give us a very good answer. But as we can see, the orange answer and the red answer are much closer to one another. What that indicates is that the answer is probably very good already, right? If we change delta x a little bit, and the answer doesn't change very much, that's pretty much telling us that if we make delta x even smaller, the answer is not going to change either, right? If we believe that the answer will eventually converge. And indeed, the answer is this red line. And as we can see, the green line is pretty much underneath the red line, right? So that's why you cannot see the green line. So we have a really good answer. Why are we interested in the exponential function? Because of this result, because the derivative of the exponential is the exponential. If you compare this red line to the blue line on top of here, right, you can see that they're pretty much the same thing. And what that is telling us is that the exponential is a very special function that satisfies that its rate of change is proportional to its value, right? In particular, in this case, the exponential, the rate of change of the exponential is the same at its value. Meaning if you wanted to figure out what the rate of change of the exponential, say, is at x equal to 1, you compute the exponential at x equal to 1, which is equal to the Euler's number, and it turns out that that is going to be equal to the slope over here of the graph. Sorry, over here, the graph, which is 2 point something. And we'll know examples like, for example, population growth of systems that behave like this, right? Where if you have a small population, it roughly behaves like that. It grows in a way that is proportional to the amount of members that there is at the population at a given time. The logarithm is the inverse of the exponential function. It's, for example, a really important function in computer science because the entropy is measured in units of the logarithm of something. The entropies are measured in bits. So if you're interested in statistical mechanics, the logarithm function is a really, really important one. And we can do this, play the exact same game. We can choose various delta x's, and as we decrease the size of delta x, the answer seems to converge to something. And it turns out that the derivative of the logarithm of x is just a function 1 over x, which is drawn in magenta here. Finally, the last example that we mentioned was this hat potential. This hat potential is a really special potential. In here, I just chose an example of it, which is this function x squared minus 1 everything squared. This is a quartic polynomial, which is why it can have this shape. And it's really important, for example, in the field of particle physics. In particle physics, this hat potential is responsible for something called spontaneous symmetry breaking. And for example, in the Higgs mechanism, that is the way that particles acquire mass. But let's stick to just studying this hat potential. And we can see that, for example, we can choose various sizes of delta x, right? And at the various sizes of delta x, we're going to have a different answer. But it turns out that all of the answers, pretty much after the blue one, which I chose a really bad delta x, all of the answers just lie underneath the exact answer, which is this purple line. Okay. And we can also understand what this answer is, right? Because, for example, in here, I hope everyone agrees that the slope is equal to 0. And in here, the derivative is equal to 0. Right? In here, for example, the slope is negative in all of this region. And indeed, in here, the derivative is negative in all of this region. In here, the slope is positive, for example, in all of this region. And indeed, in all of this region, the derivative is positive, it's bigger than 0. Right? In here, the derivative becomes 0 because there is the slope in here is 0. The slope in here is negative, which means that the derivative is negative here. And again, it becomes 0 over here because, again, we have a slope 0 here. So we could have guessed. The point here is that we could have guessed how the plot has to look. And it turns out that this plot is just some cubic function of x. Okay. Now, let's go to the big question. So I have to compute this derivative, I need to choose a step. I need to choose a delta. The question is, how do I choose that delta? Or how confident can I be on my result? And the answer is that one of the answers is that what we can do is compute the answer for various delta x's and see whether the answer will eventually converge to something. And indeed, for example, in here, I chose to compute the derivative of the sine of x at x equal to 3. Just choose some arbitrary point. And indeed, you can see that the derivative changes as we change the step, right? So in here, the derivative is too high, it's too positive. In here, it sort of overshoots and it becomes too negative. But it eventually, when delta x becomes really, really small, wants to tend to some point over here. And as long as we believe in the continuity of the function sine, and we believe that the scale in which it is continuous is bigger than the scale of this graph, we can, with a lot of confidence, assert that this is going to be the derivatives, and so minus 0.99. Now, here is a problem. Okay, this derivative did not converge very well. Okay. If I had changed to 0.2, the answer would be very different than what the actual answer was. If I changed to 0.6, it could also be very different. Now, what I want to introduce to you is a derivative, a different version of the derivative that analytically is the same, but for the computer, it's different since we cannot take the limit as delta x equal to 0. And that is called the symmetric derivative. The idea is that to compute the derivative at x, what we're going to do, what we were doing before, is that we would start at, sorry, let me write something. Let me quickly just, sorry, let me stop sharing. transfer the slides. I think I can, yeah, okay, I managed to do it. Okay. So let me just really quickly go back to the slides. So before, what we were doing was that we were we wanted to study some function, which had some plot, and to study its derivative somewhere. Let's say the function looks something like this, right? To study its derivative over here, what we would do is place ourselves here and then move a little bit to the right. So this is x, we would move a little bit to the right, x plus delta x. So we consider this point over here and draw a line between here and here, and compute the slope and make delta x really small. And our hope was that as we make delta x really small, that slope will become tangential to the graph. Now we're going to do it in a slightly different way. The way that we're going to do it now is that we're going to grab our function, situate ourselves at x, and now what we're going to do is that we're going to go a bit to the left of x and a bit to the right of x. I'm going to consider this point over here. I'm sorry, and this point over here. And then we're going to consider the slope between those 2 points. And this is the slope, right? The change in f is going to be the difference between f over here and f over here, divided by twice delta x. Why twice delta x? Because now the difference between the point here and the point here is now 2 delta x, or 2 delta x's. This is called the symmetric derivative. And as we're going to see, this has much better convergence properties. Let me show you that. Here is this. Okay, so what are the convergence properties? Well, we can just code this up just like we did before. And let me just switch over my screen. Okay, and what we can see now in here, I have a plot of the derivative of the sine of x as x equals to 3. Just like we had before for different values of delta x. Let me just put the highlighter. Sorry. I don't want the laser pointer for different values of delta x. And what we can see now is that the slope is very different. Now, as we lower delta x, we can see that instead of approaching the value sort of from below, like it was before, in here you can see that as delta x goes to 0, the value sort of goes down before it converges. Instead, we're getting a convergence that is a lot smoother in the sense that we're approaching horizontally the value of convergence. And what that means is that for bigger values of delta x than 0, we're already much closer to the solution than before, right? Because there is not a lot of change. The derivative that you see, the slope of this graph in here is 0, which means that the value of the derivative is not changing very much in the neighborhood of delta x equal to 0, right? So now we're going to do something which is a test of convergence, which we can do for the symmetric derivative, which requires a little bit of a push in abstraction. Now what we're going to do is compute the slope of this graph, meaning we're going to fix what x is. We're going to compute the derivative of x at a fixed x, and we're going to compute the derivative of that derivative with respect to the delta, with respect to the step that we do. And as we can see, that derivative goes to 0. That derivative starts being something, and then it eventually just converges down to 0. which corresponds to this converging very nice. So all in all, the symmetric derivative is going to be, for most purposes, is going to be a better approximation to the derivative than the forward derivative that we were seeing before. Okay, maybe let me stop here for a second and see if there are any questions. It's also fine if so I'm hoping that the reason that there are no questions is because everyone is understanding everything, but it's also fine if you all want me to just go back to the very basics. If the reason why there are no questions is because there are some people that are very lost, that would also be fine. Okay, then I guess let's move on. So we can do the same sort of test for example, the convergence of the exponential, and we see that the derivative converges really nicely, right? Again, we get sort of a flat graph for this derivative. And now before we move to applications, let me just mention something. If you all want a challenge exercise, the challenge is would be a really nice challenge would be to compute generically for a generic function what this slope here is. So if you take the forward derivative, a really good challenge is, can you compute what the slope is going to be? And what you're going to find, or what you should be able to find, is that this slope is actually related to the second derivative of the function. So your convergence is going to be worst if the acceleration is really high. In other words, when you have a system that is going through a really high acceleration, let's say, for example, a ball is going towards a wall and the ball crashes onto the wall, the computation of that derivative using the forward difference of the change in position when the ball hits the wall, so your ability to compute the velocity there with the forward derivative is going to be really bad. Okay, and that is because the convergence of that derivative is going to be proportional to the force, to the acceleration. If you finding the proportionality factor is a good exercise in case anyone wants to do that. Okay. Good. So now let's move over to some applications of calculus. And one of them is something that I've hinted at a lot in our development of intuition, which is optimization. And optimization is a problem that we're all very familiar with the need of it, especially maybe nowadays in the era of machine learning and artificial intelligence. And the machine learning is essentially a problem in optimization, in how do you adjust your parameters so that whatever you ask ChatGPT gives you an answer that you find acceptable, right? There is some function of you. Yeah, I'm oversimplifying here, right? But essentially, what ChatGPT wants to do is to minimize your degree of discomfort at the answer that it gives you, right? And in a certain way, that's all that we are doing when we're speaking. So minimization is a difficult it's not a difficult but an important problem And calculus is the answer to that problem. So minimization is the problem. If I give you some function that depend on some variables, what is the minimum value that that function will ever take? And as we saw in various examples, and here I have an example of the hat potential, but now this hat potential has been slanted a little bit, and I did that by adding just a linear term to the polynomial. And the point is that at the minimum, as we can see, the slope is going to be 0. So a good technique to find the minimum of a function is to compute its derivative and then check wherever the derivative is equal to 0, right? Notice that that is not a foolproof method, because there can be, for example, at the maximum of a function, the derivative is also going to be equal to 0. The slope also becomes 0, the maximum of the function. More importantly, you can also have local minima. In here, if you zoomed into this box, if you were only seeing the function over here, you might be fooled into believing that that point over there, where the derivative vanishes, is the minimum of the function. That is what we call a local minimum. A minimum, which is so that's a point which there is a neighborhood of that point in which that point is the minimum of the function in that neighborhood. So that is a local minimum. So checking that the derivative is equal to 0 is not enough to find the minimum of the function, but it's a good first step, right? There is a way of, for example, distinguishing whether that minimum is actually a minimum, a local minimum, or a local maximum. And maybe we can see that by going back to our acceleration plot. Let me just move backwards. If we look back at our harmonic oscillator example, for example, in here we have a maximum of the position, and the derivative as promised is equal to 0, right? And what we can see is that the acceleration is negative. That's very important. Let us now look at the situation a little bit forward in time. So if we let the situation go a little bit forward in time, now we can see that when we're at a minimum of the position, oh my God, I was so good at stopping that exactly at the minimum. That's a pretty horizontal slope. So the position at a minimum of the position, the velocity is again 0, as we can see here. The velocity is again 0. But now the acceleration is positive, right? So now we can see that to distinguish between minima and maxima, what we need to do is look at the second derivative. If the second derivative is negative, we're going to be at a maximum. If the second derivative is positive, we're going to be at a minimum. And why is that? Because at a minimum, what must have happened is that right behind the minimum, we must have been, let me just go a little bit behind. Right behind the minimum, we must have had a negative velocity. And right after the minimum, we must have a positive velocity, which means that the velocity itself increased. It went from negative to positive, meaning that the acceleration must have been positive. On the other hand, when we're at a maximum, we go forward. At a maximum, right behind the maximum, the velocity is positive. And right after the maximum, the velocity becomes negative, right? Which means that the velocity itself decreased, right? It went from positive to negative, which means that the acceleration must have been negative. And that's how we can distinguish between local minimum and local maximum. On the other hand, there is no local way. There is no way using calculus of distinguish, or at least differential calculus, to distinguish between whether you have a local minima and a local maximum, or whether you have a global minima or a local minimum. Because differential calculus is only sensitive to local things. It's only sensitive to what happens around this point. It cannot know, if you're interested in this point, it doesn't know anything about this. Okay, good. Now this brings us to a question. Okay, I compute f prime, I compute the derivative of f, and I now need to find where is the derivative of f equal to 0. Which brings us to the question, how do I find out the zeros of a function? If you give me a function, how do I find out where is it equal to 0? So for example, let's look at the function x cubed minus 2. This function, we're interested in knowing for which value of x, right? This function is equal to 0. And from the plot, we can sort of see that it's like 1 point, it's kind of in between 1 and 1.5. So maybe it's like 1.25, maybe from the plot. But we would like to have a better way of knowing where the function is equal to 0. And why would we be interested in that? Well, for example, what is the solution of the equation x cubed minus 2 equal to 0? That is the solution of that is x equals the cubic root of 2. And you're like, Ivan, I have a calculator. I can just compute what the cubic root of 2 is. Or I have Python. I can just ask Python what the cubic root of 2 is. But you see, somebody like Newton didn't have a calculator available, right? So they had to compute the cubic root of 2 somehow. And this is the method, the Newton-Raphson method. And this is a very beautiful method. So we're going to see it in an example, as always, instead of saying it in general, and we're going to see how it works. The trick is make an initial guess. Hopefully that guess won't be too far off. I could have guessed 1.25 from this plot, but I wanted to show you the method and how it works. And if I choose a value that is too good, it won't serve for the purposes of showing you how the method works. So I'm just going to choose a really bad value, which is 2.5. Okay, 2.5 is a horrible value, right? The function is equal to 15. It's not 0 there, right? But I'm going to choose 2.5. And then from that initial choice, start searching for the point where the function is equal to 0. The second step is I guess the first step is from that point, we're now going to compute the slope of the function at that point. And that slope is the slope of the line, which is tangent to that point. And that's what I've drawn here. This orange line is the line tangent to that point, which was my initial guess. What I want you to notice is that this line, this orange line, now intersects the x-axis at a point which is much closer to the 0 of the function than my initial guess. My initial guess was all the way over here. And now this axis that I'm approximating, this blue function by, has an x equal to 0, which is much closer than the true value. What is the idea here? The idea is that what we're doing is replacing this blue function by this orange function. So we're linearizing the function. This is called linearization. And why? Because finding the zeros of a straight line is a much simpler task. That is a task that we can do by normal multiplication and division. We don't need to know how to take square roots or anything like that to find the zero of this function. And now we can take this as our second guess and repeat from there. So now we compute the slope of the function at this point, right? We replace this blue function by this orange line, which is tangent to it, and we check where is the 0 of that orange line. And what we're seeing is that 0 is now a lot closer to the actual 0, a lot closer even than our second guess. And now we can keep going. And what this is going to do is eventually find what the position x equal to 0 is. Maybe let's code this. I guess we don't have a lot of time, and I do want to talk about integral calculus. So maybe let's go through this in the slide, and then if we have time, I'll come back and I'll code it for y'all. So how do we implement this method? Well, first of all, we choose how many iterations of the method we're going to use, how many steps we're going to use. In here, I'm going to choose only to do it 5 times. Of course, I can do it 100 times, but a computer is really good at doing this method. And I'm going to do an initial guess. I call it root because I know that the problem is solving for the cubic root of 2, so I just called it root. And this is my initial guess, which is equal to 2. And now I'm going to choose a delta, which is going to be a step size that I'm going to use to compute the derivative of the function at my guess. Now, how does the actual method work? Well, for every n in the range between 0 and the number of steps, right? So it will be 0, 1, 2, 3, 4. So n is which iteration of the method I'm doing. what I'm going to do is I'm going to compute the slope at the root, right? This is the slope. And then I'm going to compute the intersection of that tangent line with the x-axis. And in here, this turns out to be the formula for the intersection. This is an easy formula to derive, but that is a really good exercise too. I highly encourage you all, if you want to understand this method, to prove that this is the formula for the intersection of a line with a given slope and the x-axis. And then what I'm going to do is I'm going to save that new intersection as my new root for the next step. So I'm updating the value of the root. I'm updating my guess. And then at the end of the day, after doing this for 5 steps, the result that we got for the root is 1.2599. And if we check against the actual answer, that turns out to be off by less than 0.0000%. So we essentially got the answer to, I guess, 6 significant figures. Okay. By only doing this method 5 times. So this is really powerful stuff, and this is a way that Newton and people before calculators could compute this sort of solutions to the square root and cubic root and so on. Okay, so let's now look at our final subject. We have 7 minutes for this, but I don't want to go too into detail with it, which is now a different problem. I want you all to forget what the problem that we were studying before is, the problem of finding slopes. Now we have a different problem. Let's say I give you some function, let's say the sine of x, and I'm interested in this function in some finite interval between 0 and let's say 2 pi, right? Which is 2.1415. Okay, so we got a question on the failure of Newton-Raphson. I guess if it doesn't converge, right? If after, what you can do is plot just like we were plotting the derivative before, and for different steps. In this case, it will be for a different number of steps. And let's see, and you should see whether the method is converging somewhere. And the good thing is that you can also check at the end of the day if you're once you have a result, you can just put it inside of the function and check whether it's actually equal to 0 or not. Now the function is the method is guaranteed to converge as long as you start with a good enough initial guess if the function is smooth. Okay, yeah. Okay, good. So let's keep moving now to integral calculus. Yeah, so the question is, what is the area underneath the curve? And this is actually a really old question that the ancient Greeks asked, and we're able to answer it. And the basic idea of the answer is the following: let's break up this interval from 0 to 2 pi into little sub-intervals. And here I chose 5 sub-intervals, 4 sub-intervals. What we can do is instead of approximate the area between here and here by the rectangle that goes between this point and this point, between this interval and this interval. As you can see, this is a really poor approximation, but if I choose to divide my interval in a finer way, we can see that now we're getting a better approximation to the area, right? In here, I'm overestimating a little bit. This bit shouldn't be, but in here, I'm underestimating a little bit. And if we chose an even finer distribution, now we can see that we're really hitting the ballpark, right? Like the overestimations here are really, really small, and the underestimations here are really, really small. Now you can imagine that this is not too hard to code, and what we can do is check how the area changes as we change the number of intervals that we're dividing this into. So for this sine, this is how the area converges, and we can see that this area is sort of converging to something close to 2. And indeed, if you look up, the area of the sine function between 0 and 2 pi is equal to 2. This area, we give it this funny name. We call it the integral between a and b of the function f of x. That's this area. With a small caveat. In the case of the sine function between 0 and 2 pi, the sine function is always positive. So that really is the area. If the function becomes negative, we're going to count that area as negative. Okay, and that's what we call the integral of a function. Now, I should say, unlike derivatives, which were at a point, they're local, integrals are global functions, meaning that integrals depend on on all of the values of the function between a and b. And that makes the problem of computing integrals a lot harder than the problem of computing derivatives in particular. In general, if you give me some function f of x, I am not going to be able to integrate it for you. It's just a fact of life. Okay, and there will not be a closed form expression for that integral. So in here, it's really necessary for us to develop some computational methods to compute this integral. And indeed, we can just code up these squares, right? That's one possible way of doing it. So let me now show you just a simple example to develop some intuition. What I'm going to do here is plot the cosine of x as a function of x. And what I'm going to do is plot underneath here the integral of that cosine of x, so the area under the curve. But notice I'm going to integrate up to x, meaning for example, at x equal to over here, what I mean is that this value here is the area underneath the curve from 0 all the way to here. Okay, and that's how I made it a function of x. And let's see how that changes. Well, if we start at the beginning, right? We start over here, and as we move along x, we're sweeping more and more areas. So the integral is becoming positive and positive and positive until it reaches a maximum. And it reaches a maximum because in here the function becomes negative, and it starts and the area starts becoming negative, which means that the integral is going to start decreasing, because now we start adding some negative area. The integral is decreasing, 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 decreasing. And over here, we can see that the area that we accumulated at the beginning that was positive, now we've canceled by area that we've accumulated, which is negative, and indeed the integral is equal to 0 now. Now we're going to keep accumulating some negative area, making the integral very small, right? And here the integral is very small. And in here, when we reach a minimum of the integral, then this function is going to become 0 again, because now the area is going to become positive. And you see, now we're getting positive area. So our integral is increasing, is increasing, is increasing, is increasing. And then the integral became positive. And now the integral reaches a maximum, which is where this function is equal to 0. Okay, so hopefully this will help you develop some intuition for what the integral means. But also notice something. Whenever we are at a maximum of the integral, the function is equal to 0. Which means that which it suggests something, which is that the derivative of the integral, which should be equal to 0 at a maximum, is equal to this function, because this function is equal to 0. In other words, the derivative of the integral of a function is just the function. And indeed, we can check that. In the case of the sine function, for example, if we take the function and then we compute its velocity, which is this cosine function, and we can compute the integral of this cosine function, and what you're going to see is that this integral is equal to the original function. Okay, this is called the fundamental theorem of calculus, and it's probably one of the most important results of mathematics, along with Stokes' theorem and its generalization to higher dimensions. But it's clear what the intuition is, and if we had a little bit of more time, I could prove it to you. But I think this is good, and probably the intuition is good enough. Okay, so I guess we're done. This was it for calculus. I hope that you all enjoyed it, and yeah. Are there any final questions? That question on the of convergence of Newton-Raphson. Oh, I was just about to ask Declan and Adriana to see if they had something to say, but Declan did mention something, which is right. So Declan made a really good point, which is that if the function is it has many zeros, in general, if you start with an initial guess, which zero are you going to end up with, right? And in general, the intuition is that you're going to end up with the zero that is closest to your initial guess. Okay, that's a really good point. Oh, thank you very much for thinking, and thank you for attending to the lectures. Okay, any other questions? I hope that this was all followable and not too confusing. Developing intuition can be a really confusing thing to do in general, but it's good to look at different examples. So, okay, any questions? Okay, awesome. Thank you. And maybe I should just tell you all, feel free to look me up online and send me a message. And if you're more interested in these subjects, and I guess I am a mathematical physicist, at least in upbringing. So I am really interested in the connection between mathematics and physics, and in case anyone wants to know more about it. And yeah. Good luck with the rest of the course, and yeah, thanks for being part of REYES. Okay, thank you, Declan. Thank you, Adriana, for helping me out, and see you all later. Bye. Thank you, Beth, for your help.
You're welcome. On the schedule I have, it was like till 2.
Oh, really?
Yeah.
Oh, I was under the impression that it was.
That's all right.
Hour.
Hey, Tom, the webinar's ending. Yeah, no problem. Yeah,
Okay,
I thought it was going
bye.
till 2, but yeah, that's cool. I'm talking to him on the phone.
Oh, okay.
Yeah.
Okay, good. Okay.
Thank you, sir.
Okay, goodbye.
Yeah, I didn't have host, so I couldn't end it. So I had to get a hold of Tom.
I see. I see.
Yes,
Okay.
bye.
Okay, thank you, Beth. Bye.
You're very welcome.